Welcome back. In the last video, we prepared data loaders for our EffNetB2 feature extractor, and I left issuing you the challenge to train one. How did you go? Did you set up a loss function, an optimizer, a training function from engine.py? I hope you gave it a crack, but if not, let's now do it together. From going modular, we need our training function from engine.py. So that lives in goingmodular.goingmodular. Import engine. Of course, we created this function way back in section 5. And we have here, this is engine.py, which of course lives on GitHub under going modular under engine.py. That way we don't have to rewrite all of the training code that's in here and testing code. We can just call this function. Very helpful. So we've got engine, now we've got our loss function. What are we going to use for our loss function? Well, because we're working with multi-class classification, we want a cross entropy loss and an optimizer. What's our optimizer going to be? Well, we're going to use the ever faithful Atom optimizer. You could also use something like SGD. There's a lot more in the torch.optim package, but Atom seems to be working quite well for us. And we want to optimize the parameters for EffNetB2. And we'll set the learning rate equal to 1e -3. That's a pretty good learning rate to start with. Of course, you could adjust this as a hyperparameter that you can change. And let's set up our training function, hey? We'll set the seeds first so we can get as close as possible to the same results on my screen as your screen. Again, don't worry too much if our numbers are slightly off. That's due to the inherent randomness of machine learning. So model equals EffNetB2. We're going to set up, so this is our .train function from engine, which is, of course, right here. And this is in engine.py. So the train data loader is going to be what? It's going to be the data loader that we created before, EffNetB2. And then the test data loader is going to be what? Of course, it's going to be the test data loader for EffNetB2 that we created above. This just ensures that our data is transformed using the EffNetB2 transforms. Then what else do we need here? Epochs. How long should we train our model for? We want it to perform pretty well, but we also don't want our model to be training all day just yet. We could do that later on if we wanted to. But because we're working together here, we don't want to be waiting all day for our model to train. So we'll keep our training time relatively short again. If we go into PyTorch experiment tracking, what was our best performing model? Setting up a series of modeling experiments. What did we have? Comparing. There we go. View the experiments. Which one performed best? Okay. 10 epochs. And there's EffNetB2 as well. 10 epochs. So I think that was our best performing model. Yeah, there we go. 10 epochs. So that was from PyTorch experiment tracking. I think 10 epochs should be enough. That's a good balance between not too long, not too short. So 10, of course, if you wanted to extend this project, I'd encourage you to train for a little bit longer if you wanted to try that out. What else do we need in here? We need an optimizer. We've just set that up above. Optimizer. We need our loss function to measure how wrong our model's predictions are. And then we're going to set the device equal to the device. So because we've set up device agnostic code, this will use the GPU if it's available. So you ready? Let's train our first Food Vision Mini model deployment model candidate. That was a bit of a mouthful. Now this should be quite quick. Let's see how fast this goes. Oh, very nice. Only about 6 seconds per epoch on my Google Colab instance. I'm not sure what GPU I have. Now, once again, just a reminder, don't worry too much if your numbers aren't exactly the same. What we're looking for more so is directionality. And what I mean by that is your test accuracy should be going up, or it should be around this level. It doesn't matter if the 4.3 is slightly different. Same thing with the test loss. It should be going down. So I'm just going to check what GPU I have. Look at this. Our model is performing 97% or thereabouts test accuracy after 6 epochs. How good is that? That's the power of transfer learning. We're watching a model training in real time. And I'm continually amazed because this sort of stuff wasn't possible 5, 10 years ago. And we're just doing it with a few lines of code. And there we go. How good is that? Our model performs on the test data set at nearly 97% accuracy. That is completely in line with what we said we wanted one of our goals to be. Performs well, 95+% accuracy. Well, we've got that. Now we just need to measure how fast or how long it takes to make a prediction. We're going to cover that later on. So let's just go down here. This is the GPU I have. I have a Tesla P100, so just keep in mind that if you have a different GPU, you might likely get different training times here. I'm of course paying for Google Colab Pro because I've found it to be very worth it because you get upgraded hardware, faster model training, faster experiments. You can figure out what doesn't work quicker, so you can move closer towards what does work. Now, while we're here, I was going to make it another video, but since that video went quite quick, let's inspect our model's loss curves, because the numbers on the page look pretty good. But you know the data visualizers motto? Visualize, visualize, visualize. And we have a helper functions.py, and we have a beautiful function in here called plot loss curves. So we've already imported helper functions.py. It's going to be right here. So let's check it out. Helper functions, import plot loss curves. And this is why we save our model's training results to a dictionary. Now, of course, we could track these in TensorBoard or something like that if we wanted to build more modeling experiments. But because we're only doing 2 major modeling experiments in this notebook, we can inspect our experiments manually. So let's go plot loss curves and check them out. EffNetB2 results. How do they look? Oh my goodness, they are some good looking loss curves. Losses going down, accuracy going up, just exactly what we want. In fact, we have a test loss that is lower than the training loss. What does this mean? So let me just link in here. Section 4 or chapter 4. Now I believe it was section 8 in here where we covered what should an ideal loss curve look like. Now I don't know if we've covered, see here for what an ideal loss curve should look like. I don't know if we've covered what happens if your test loss is lower than the training loss. We've kind of hinted that if training loss is lower than test loss, your model is generally overfitting the training data set. But here, this is giving us an indication that if we kept training our model for longer, these 2 curves should line up and we would actually get even better results. Now, that's not always guaranteed, it's just hinting at that. So the next thing I would try to do here is maybe train for longer and add a little bit of data augmentation to our data loaders. So you could use PyTorch state-of-the-art recipe. I believe they used, we might have covered this before, they used, if we go down here, trivial augment, which is a type of data augmentation. So they're the first 2 things I would try out. Train for longer, add data augmentation if you'd like to extend this. And in fact, if you do, please let me know how you go. I'd love to see your results. But for now, this model is more than enough. It satisfies our first criteria because what we're trying to do is deploy a model as fast as possible so we can test it out. So we've got this. Let's keep going. We're going to collect some statistics about our model so that we can compare it to our VIT feature extractor later on. We'll do that in the next video. But for now, our EffNetB2 feature extractor is performing quite well.